All right, so we're talking about increasing and decreasing. All right, increasing and decreasing functions or ranges of functions are dealing with the portion of the function where we're going up or we're going down. Okay? Now, if you take a look at these two graphs here, we have y equals x squared. You'll notice there's a point here at the vertex where everything to the left of that, it was decreasing. It was on its way down. And then once we pass that point, it's now increasing. Okay? So what we would say is it would be decreasing from negative infinity up to 0, but not including 0. Okay, we'll talk about that 0 in a sec. It's increasing.
It doesn't include 0 because it's a whole, right?
Well, no, that's just how they indicate the origin. I get what you're saying there. From 0 to positive infinity. Okay? Now, as you can see here on the other one, they give us, in this case, some sort of a cubic here, where we've got a point where we've got a highest point and we've got a lowest point. Everything to the left, this thing is going up. So there's an interval where it is increasing from negative infinity up to negative 1. Okay?
Then decreasing from 3 to 0.
Well,
Or
it's
from
decreasing
negative
from, it's decreasing from negative 1 all the way over to 2.
Oh.
We're talking about the x values. Okay? And then it starts to increase again from 2 up to infinity. Okay? Now, think about this here. We're talking about something that is changing. And we're talking about how it's changing. All right? That has to do with our velocity or our rate of change, which is slope. Okay? Now think about this. If I am increasing, what do you think that says about my slope?
Positive.
It's positive, which means our derivative is
Positive.
positive. If it's decreasing, that means our derivative would be negative. Okay? So you're making that, you're seeing that. Here what I want to show you, what does this mean for our derivative? Our function, okay, our derivative f prime of x, that 0 in this case is kind of the boundary, and we'll talk about that. That's what's known as a critical value. But our derivative will be negative to the left of 0, and it will be positive to the right of 0. Okay? This is what's known as a sign diagram. We're going to be doing lots of them. Okay? Over here, for f prime of x, we have two different critical values at negative 1 and 2. The derivative is positive to the left of negative 1. It's negative between the two, and then it's positive again. Okay? So that's how this increasing and decreasing relates to our derivative. Increasing means positive, decreasing means negative. So, pretty simple so far, right? Not too bad.
So far.
All right. Now, some functions don't change. Some functions, like these exponential functions, we have an exponential growth function, okay? And then we have an exponential decay function. Sometimes we can have functions that always are increasing. We call them monotone increasing, or also sometimes your book will use strictly increasing. So strictly or monotone just means it's always increasing. If it's always decreasing, we could say it's monotone decreasing or strictly decreasing. Okay, so that's just a term I wanted to throw out there so that you've heard it before if you happen to see it. We don't do a ton with that specifically though. So let's talk about those sign diagrams, okay? We were given the actual points here, and in this example here we have f of x equals x cubed minus 3x plus 4, okay? You'll notice here the diagram that we were given identifies x equals -1 as the point where we have that max, okay? We could even plug in -1. -1 plus 3 plus 4 would be 6. So that's the point -1, 6. That's going to be the maximum point, okay? It also identifies 1 as the point where we have a minimum point. So 1 minus 3 is -2 plus 4 is 2. So there's our point 1, 2. That's a min. Okay? And that's a max. Now notice here, to the left, our tangent lines, i.e. our derivative, all have positive slopes. Hence, you notice we put the two critical values, the -1 and the 1, on a number line, and to the left we identify that our derivative is positive. Okay? Between -1 and 1 our derivative is negative, and after we get past 1 our derivative is positive. Okay? From that we can tell this down here. It's increasing on the interval from -infinity up to -1, okay? And from 1 up to positive infinity, okay? And, oh, that's a typo. These should be parentheses.
So it's not including -1.
Yes.
Decreasing, it's including.
And I do want you to do parentheses. Honestly though, IB does not make a huge difference of this, but if you go on to AP, they do. Okay? And IB is not always consistent. I've seen some mark schemes where they take off for it, and some mark schemes where they don't. So, unfortunately, it's a little inconsistent. So let's just do it properly all the time.
It's not including in any of them? In any of them?
No, because of what we're about to look at, okay? I've been using the term critical values, okay? Where did that -1 and +1 come from? That -1 and +1 are the critical values. If you looked at the graph, those were the max and min points, and what did we say already even that happens to our derivative at a max or a min point?
It equals 0.
The derivative is 0. We have a horizontal tangent. So if it equals 0, it's not positive or negative, right? So that's the moment when we're not increasing anymore, but we're not decreasing either. We're just stationary for that moment. Okay? The rate of change is 0. Okay?
How would it be a tangent if, for example, on the graph that we did earlier where it's kind of looks like a sine curve, like that one right there?
Yeah.
How would it be a point of tangency if you draw a line or connect it?
Well, remember, we said tangent in our context is different than tangent back in geometry with circles, because these can like fold back on each other, and that's the application we were just doing earlier, where we have a tangent. Where does it hit the curve again? Okay, this is like we're riding along a road, out in the
So technically it's
dune
not-
buggy or something, and we slide off the road. So we know the road hits back again somewhere up here, so since we're already off-roading anyways, rather than make our way back here, we just keep going in a straight line, and we know we'll hit it again eventually. But we are going off initially on a path that is tangent to our curve, okay? Now, these critical values are the values where the tangents are horizontal, okay? So, the slope equals 0, i.e. f prime of 1, in this case, equals 0. here the slope equals 0. So f prime of the -1 equaled 0. And you'll notice here, they came from setting this derivative equal to 0 and then solving for x. That's something that we have done a number of times already, and not kind of without much reason why we were doing it, but now we know why.
Are we gonna do angles now?
Okay?
Is that where we're heading with this?
Angles?
Yeah.
Not
Because of
really.
parallel lines?
Oh, no. Not this year, maybe. Okay, so we have the sign diagram, but here's the key. Before you can make your sign diagram, you have to identify the critical values that create the different intervals on the sign diagram. Okay? So, here's what we were just looking at on that homework problem. It's the same function we just had. We have y equals x cubed. So we've got that, we've got that, we've got that, we've got that. So we have this function here. And
They're not maximum.
if you set the derivative equal to 0, yeah, you can see here, we do not have a max or min point here. Okay? However, if you set this equal to 0, what do you get for your critical value? 0. Okay? Oh, by the way, I forgot to point this out. Your book uses, and IB uses the term stationary points a lot. They use both terms. They use stationary points as well. So for the points that you get for the critical values, and they call them stationary points because your velocity is 0. You're stationary. You're not moving for that one moment. Okay. But notice here, if I make a sign diagram, getting back to this, I'm increasing on the left and I'm increasing on the right. Okay? So we could say that this is increasing for all values except for 0. Okay? So, what we call these are plateau points. A plateau, if you know your geography, is a part where it may be hilly, but it levels off. Okay? It's just a level place of ground. Here, we were increasing, and it leveled off for that moment. We have a horizontal tangent. Okay, and I know it's kind of goofy to think of a tangent line going straight through the function, but it is, okay, at that one moment. Okay? I know we're hitting a lot of terminology here, but you'll get used to it. We're going to use it a ton. So, let's kind of take a problem, kind of start to finish, and look at what we can do with this. Okay? Alright, so we need to find the intervals where f of x is increasing or decreasing if f of x is x cubed plus 5x squared minus 4x minus 20. Find the critical points and classify them as max, min, or plateau points. Okay? So, if I'm finding critical points, first thing I'm going to do is, before that, when in doubt, oh, come on. Find the derivative. When in doubt, find the derivative, okay?
That's the terrible way.
So f prime of x is 3x squared plus 10x minus 4. And to find critical points, we've got to do what with this?
Set it equal to 0.
Set it equal to 0.
That's the same thing.
Okay? Well, we're going to factor now that we have it equal to 0,
Okay.
if we can. Okay? So we see if we can factor. Can't factor?
No.
Well, that's fun. So,
Agreed.
we get x equal to a negative 10 plus or minus the square root of 100 plus 16 times 3 is 48 all over 6. Okay? So we have 148, that's 74, that's 37, so that's 2 root 37.
You just did that in your head.
Yeah, I'm done.
You just divide by 2 twice.
Come on.
Okay.
Easy.
So that's negative 5 plus or minus root 37
Are we just gonna pretend that?
all over 6. Oh wait, not over 6. Over 3.
You just did like the whole
So.
quadratic formula in his head.
Okay.
Alright, so now that we have the critical values here, we can plug them into our original function. Okay? And by the way, don't forget on the calculator, it is, there are easier ways to actually do this. Just to review real quickly, if I have negative 5 plus the square root of 37 divided by 3, and I store that in x, remember I can simply type in that function. Okay, it was x cubed, someone help me out, was it minus, what?
Plus 5x squared
Okay, plus 5x squared
minus 4x.
minus
Minus
20. Okay. So there we have negative 20.74. Okay. So now I know that 1 point on our graph, and it is a critical point. All right. All of these are critical points, but it might be a max, it might be a min, or it might be a plateau point. Okay. So we have the 0.36. And we got negative 20.7. Okay? Now, if we do the, if we do the same thing, again, this is where your calculator is nice, so we just have to do this, but we've got to do minus the square root of 37. We've got to reevaluate this function, okay, and we get 12.6. Okay, so at negative 3.69, we have a positive 12.6. Now it seems as though those would be min points and max points, okay? But the way we can confirm this is with a sign diagram. If you remember what we were doing a little bit last week, we have, or earlier, we have our critical values, so negative 3.69 and a positive 0.36. And to make our sign diagram, you can pick any number you want in those ranges, okay? Anything below negative 3.69, anything between the two critical values, and then anything above. So, and we plug those into the derivative. So I would test f prime of 0, f prime of 1, and I would test f prime of, say, negative 4, okay? You don't have to pick those values exactly, but if you can pick 0 and 1, go for it. Okay. If I plug in 0 into the derivative, I get a negative, which is really all I care about. I don't care what the actual value is. I just know I get a negative. If I plug in 1, I have 3 times 1 plus 10 times 1 minus 4, which is positive. So I got a positive there. And if I plug in a negative 4, I have 3 times 16, which is 48, plus 10 times negative 4 is negative 40. So 48 minus 40 is 8, minus 4 is 8. It's positive. So what I have here, you'll notice I was increasing to the left of negative 3.69, and I'm decreasing after negative 3.69. So what must that critical point at negative 3.69 be? It's a max. Okay? And by the way, if you are told to show something as a max point, this is how you could do it. You could say because it changes from increasing to decreasing at that critical value. Basically 2 things. Prove it's a critical value, and then show that it changes from increasing to decreasing. Okay? We'll do more of that later. So again, that gives us a max point. And then notice at 0.36 it goes from decreasing to increasing. So that's going to make it a min point.
What would the sign diagram for plateau points look like?
It would be something, it would say, like if the 0.36 gave us a plateau, we would be decreasing, and then it would continue to decrease afterwards. Okay. Now, this all has told us a bunch of stuff so far. We can factor the original function. As you can see here, I went through the factoring by grouping. And when we factor the original function, we can get the zeros. We know the zeros of this function are going to be at x equals a negative 5, and then also plus or minus 2. Okay? So, as we look at that, we can plug in, here's negative 2, positive 2, and negative 5. We have a critical value, a min point at 3.36, negative 20.7, so it's going to be somewhere way down here. Okay, and obviously that's not quite negative 20, but that's far enough. And we'd have a y-intercept at negative 20. Okay, so there's our negative 20. And this is that 0.36 negative 20.7. Okay, which is our min. And then we had a max at the negative 0.369, 12.6. Okay, negative 123.69. So somewhere around here at 12.6. Okay. And now we can have an even more accurate graph. Okay, so we know it's going to be a min there. By the way, if it's supposed to be a min, make sure you're drawing it neatly so it is a min. Don't hit your min and then keep going. Or hit your max and keep going. Alright, so we've got that. We hit our y-intercept. We come up here. And that is approximately what that would look like.
Where did you get the... Oh, it's the... On the x-intercept... On the x-axis, it's the +2, the -2, and the -5 is what you got.
Yeah.
2 points.
Yeah, those were our zeros. Okay? Alright, so that is one of the things that we want to do here with our derivative. Give us more precise. We already did last year the part of graphing, getting the zeros, the y-intercept, using the leading coefficient test to tell whether it's gonna be going up on the right or down on the right. Now it's just even more information we can tell to get a more precise graph. Okay? Any questions? All right.